All right, so let's take a look at rocket engines, and we're going to do the energy balance, derive equations for the exit velocity, so we can then calculate thrust performances, and then we can calculate engine performance, and we can actually find the area of the throat, okay, and the exit. All right, so here is a rocket engine. Crude idea. Okay. This is the exit. Here's the throat. And what I'm going to do is inside here state 2, so maybe here, and then state 1 kind of in here, okay? And I'll talk about this. Propellant in, you got QR, and the throat, remember, is always the star values because it's choked. So, perfect gas, perfect gas, constant pressure, heat addition. We're going to assume 1D motion. We're going to assume 1D motion. Isentropic. Steady state. And it's supersonic at the exit with no shocks in there. Okay, so if you remember from a converging, diverging, a shock could show up. But in this case, we have no shocks in here. All right, so the way I'm going to do this is let's look at 1 to 2. State 1 to 2. We're going to do an energy balance. Okay, so dE dt equals q dot net plus w dot net plus the summation of m dot in h plus v squared over 2 plus gz minus summation of m dot out in its terms. Okay, so let's cancel some stuff. This is 0 because it's steady state. There's no mechanical work. The velocity and elevation changes are 0. So technically, if these are 0, then this term you can switch to h naught because that's the definition of stagnation enthalpy. So we have 0 equals mass of the propellant times QR for the heat transfer plus 0 plus m dot of the propellant times h naught 1 minus mass of the propellant times h naught 2. Okay, mass of the propellants cancel, so you end up getting 0 equals QR plus, I'm going to switch this to CP T naught 1 minus CP T naught 2, and we're going to solve for T naught 2, which will be used in the exit velocity equation. QR over CP plus T naught 1. Okay, now let's move on. State 2 to E, the exit. Okay, we'll do energy balance again. Summation of m dot h plus v squared over 2 plus gz. This is n minus summation of m dot h plus v squared over 2 plus gz. And this is out. Again, there's no mechanical work. There's no heat transfer. It's steady state. Elevation changes are gone. This velocity at 2, again, is 0. All right. So this term right here, you'll see becomes h naught 2. Okay, just like above. Oh, just like above. So 0, 0 plus 0 plus m dot of the propellant times h naught 2 minus m of the propellant, m dot of the propellant, he plus ue squared over 2. All right, we end up getting ue squared over 2 equals h naught 2 minus h2, because the propellant mass of the propellant cancels. This can be Cp of T naught 2 minus T at the exit, Te. You write this as Ue equals 2 Cp. I'm going to factor out a T naught 2, 1 minus Te over T naught 2, and then this whole thing is the square root. Okay? Why did I do that? Because from isentropic equations, Te over T naught 2 equals Pe over P naught 2 raised to the gamma minus 1 over gamma. And we're going to plug that into here. So we got Ue equals square root 2 Cp T naught 2 1 minus Pe over P naught 2 raised to the gamma minus 1 over gamma. And now we have our exit velocity. Okay, so we have Pe over P naught 2. Okay, we're assuming that the exit pressure is atmospheric, and this will actually be P naught 1, because P naught 1 will equal P naught 2 and will equal P naught at the exit because of isentropic. We're assuming no losses. Okay? All right, so mass flow rate at throat. Those are star values. And I'm just going to give you the equation because there's a lot of steps. And I may make a video at some point showing you how this is derived. But just go ahead and use this right now. A star P naught 2 over square root of R T naught 2 times the square root of gamma 2 over gamma plus 1. Oops, let me fix that. Gamma plus 1 raised to the gamma plus 1 over gamma minus 1. And then therefore A star equals pi R star squared, which is pi d squared 2 over 4. Okay? So we can basically solve for A star if we know the mass flow rate. All right? Which you're kind of sizing this rocket. Now, one thing I want to remind you of, thrust. Remember? We'll call T is m dot the exit times UE of the exit. Okay? Assuming that the exit pressure, so PE equals atmospheric, and we have no in velocity, right? So that's why it's just mass flow rate times the exit. So if I give you thrust, a large number of thrust, we can find our exit velocity from above, right here. Oops, sorry. We can solve for m dot, which we can then plug into here to solve for A star. Okay. Then if we want to know, again, this is a lot of derivation. I may make a video on how to find this one. But at the exit, you can find this exit area, AE over A star, which is 1 over ME, bracket, 2 over gamma plus 1, 1 plus gamma minus 1 over 2, ME squared, bracket, gamma plus 1 over 2, gamma minus 1. Okay? So you can use this to find the area of the exit knowing your A star. You also have to know your m dot E. Remember, Mach number is UE over the speed of sound at the exit, which is square root of gamma R TE. So you can find TE based on this equation right here.